For a function y equal f of x, we know that the derivative f prime of x tells us about the rate of change of y with respect to x, which has helped us in the past and will help us in the future to locate intervals over which a function is increasing or decreasing. It turns out that locating the intervals on which the derivative of f prime increases or decreases, that can also tell us something important about the original function f. I want to emphasize here that we're talking about the rate of change of the derivative, not the rate of change of the original function, but the rate of change of the derivative of the original function, which is the second derivative of the original function f. In particular, we're going to find out that the second derivative of f tells us where the graph of f curves upward or downward. That property of curving upward or downward is called concavity. To give you a formal definition of concavity, if you have a differentiable function f on some open interval, the graph of f is concave up on the interval when the derivative is increasing on this interval, and is concave down on the interval when the derivative is decreasing on the interval. Not whether the function is increasing or decreasing, but whether the function's derivative is increasing or decreasing. The most important thing to remember here, and I'll say again, is that when we talk about concavity, we're talking about taking the derivative of the derivative, which is the second derivative of the original function. Before we delve into the details of finding intervals where functions have concavity changes, let's take a moment to focus on what concave up and concave down look like visually. For example, if I take this curve, you notice that if you start drawing tangent lines to that curve, you see that they all fall underneath the curve. So we can think about a graph of a function over an interval. The graph is concave up if it lies above its tangent lines. Or another way to say that is that the tangent lines lie below the curve. That's a region where the function is concave up. Some people say it this way, that over an interval where a function is concave up, it holds water. And you can sort of see what they're talking about there. On the other hand, if you've got a function and you're looking at it over an interval where the curve lies below its tangent lines, or again, you could say that in the reverse, that the tangent lines lie above the curve, that's an area or an interval where the function is concave down. And again, some people would describe that as saying that the function spills water. I think it's pretty obvious, holds water versus spills water. It's probably a good way to think about concavity. Now, obviously, we're going to want to find the intervals where this concavity happens. And we'll end up using the second derivative to find those intervals as follows. There's a test for concavity. If you have a function whose second derivative exists on some open interval, call it I, if the second derivative is greater than 0, that means the second derivative is positive for everything on that interval I, then the function is concave up on that interval I. On the other hand, if the second derivative is less than 0, which means it's negative for all values in that interval I, then the function is concave down on that interval. So the second derivative tells you about concavity. A positive second derivative gives you an interval of concave up behavior, and a second derivative being negative over an interval gives you an interval of concave down behavior. In practical terms, I'm going to give you some guidelines that will help you get through this in terms of just solving problems. First of all, you'll want to locate the x values in which the second derivative is either 0 or the second derivative is undefined. Think back when you were doing increasing and decreasing. You were doing that with the first derivative. Now you just extend that same procedure to the second derivative, where the second derivative is 0 or the second derivative is undefined. Then you'll use those x values to determine the test intervals. Again, think back to when you did increasing and decreasing intervals. That's exactly what you did. You were doing it with the first derivative. Here we're doing it with the second derivative. And finally, test the sign of the second derivative in each interval determined by step 2, and then build a concavity chart. Thinking back to what you were doing with increasing, decreasing, you were doing this with the first derivative, what we call critical numbers, and you were building an increasing, decreasing chart. Now you're doing it with the second derivative, and you're building something I will call a concavity chart. Let's look at a simple example which shows us how this test for concavity works in practice. Suppose I start off with the guidelines that we just talked about, locating the x values where the second derivative is 0 or undefined, using those x values to find our test intervals, and then testing those signs in those test intervals to build a concavity chart. Those are the things we talked about doing. Let's apply them to a really simple problem. Suppose I ask you to find the open intervals on which the graph of f of x is equal to minus x cubed plus 3x squared minus 4 is concave up or concave down. This is a simple polynomial function. As we've talked about all semester, whenever you're dealing with polynomial functions, everything works out nicely. Derivatives are easy. There aren't any values where the derivatives are undefined, so you don't have to worry about where the derivatives are 0. So a polynomial function is the perfect example to start off with as being a very basic problem to see if you understand the concept. So in any case, the first thing we do is find the first derivative, because we can't get to the second derivative without finding the first derivative. So the derivative, the first derivative of minus x cubed plus 3x squared minus 4 is minus 3x squared plus 6x. Remember, we're going for the second derivative, so now we take the second derivative. That would be minus 6x plus 6. And then we want to know where the second derivative of the function is either 0 or undefined. As I just said, for polynomial functions, there aren't any undefined values, so we're strictly looking at where the second derivative is 0. So if you set that equal to 0 and solve for x, you'll find out in this particular problem, there's only one value where the second derivative is equal to 0. What do you do with it? You take that and put it on a number line. You want to determine your test interval. So since you only have one value, that means there's going to be one interval to the left of 1 that you have to test and one interval to the right of 1 that you have to test. So what do? You take a test value to the left of 1, say maybe 0. Take a test value to the right of 1, say maybe 2. How do you test them? Remember, we're testing for concavity. That's a test involving the second derivative. So you take each of those test values and plug them into the second derivative, not the first derivative. The first derivative tells you about increasing, decreasing. Here we're thinking about concavity. So if you take the test value 0, plug it into the second derivative, you get 6. Well, 6, of course, is a positive number. Positive means that the function is concave up or holding water. So you might label it that way, concave up to the left of 1. Then you move to your test value on the right side of 1, which we chose as 2. Plug that in, do the arithmetic, and you end up with minus 12 plus 6, which is obviously negative. That's concave down. So to the right of 1, the function is concave down. Since there's only one number to test, that means you only have to test for 2 intervals. So to wrap it up, what you've shown is that the function is concave up to the left of 1, that's minus infinity to 1, and it's concave down to the right of 1, that's 1 to infinity. Keep in mind that you have to be able to do a problem like this just to make sure you understand the basics, the principles. If you can understand this problem, you're in a good position to go on to hard problems where maybe the algebra is a little more challenging or something like that. But until you feel like you can do this problem in your sleep, there's no sense in moving forward with more difficult problems where the algebra might be more challenging or there might be something else that puts a little twist in it. You have to understand this. So spend a lot of time thinking about this problem and similar problems and make sure you can handle these before you try to tackle the others. And as a matter of fact, if you look at your homework, there are quite a number of problems on your homework that you'll be able to tackle just at this level without even worrying about the difficulties. You won't get 100%, maybe you won't even get 85%, but you can do quite a bit of the work because this is the basic idea. And if you've got this, you're well on your way to doing well in this section. I do want to contrast that with an example where there might be some more difficulties though. So I'm going to try a similar problem now, at least the calculus is similar, where the algebra is more challenging though. But remember, it's the algebra that makes the problem more challenging, not the calculus. The calculus steps are exactly the same. And that's what I want you to understand. You've got to get the concepts in hand and well understood before you can even think about tackling the problems where you have other difficulties that come into play. Suppose I gave you the function f of x equals 6 over the quantity x squared plus 3 and ask you to find the open intervals on which the function is concave up or concave down. First thing you'll do is find the second derivative. In order to do that, I would rewrite that function as 6 times the quantity x squared plus 3 to the negative 1. If you don't, you'll end up using the quotient rule on the original function, which works, but this is, I think most people would think, is much easier to do it as a general power rule problem. So if you're going to do it as a general power rule problem, which is my suggestion, rewrite the function as a negative exponent, then use the general power rule. So you got minus 1 times 6, write the base down, drop the exponent by 1, minus 1 is minus 2, and then you come back and you multiply by the derivative of the base, which is the 2x. Simplifying that a little bit and changing it back to a positive exponent, the negative 6 times the 2x will be negative 12x in the numerator, and if you take that negative exponent and drop it into the denominator, you'll get the quantity x squared plus 3 squared. Now I want to take the second derivative, which is the derivative of the derivative. The first derivative is a quotient rule. Notice if I hadn't rewritten it with a positive exponent, it would have been a product rule. But it would have been a product rule with a negative exponent, which again would work. But when I get something that complicated, I'll tend to change it back to positive exponents, even if that means using the quotient rule. This is something that you have to go through yourself as you're working these problems and decide which way you want to do it so that you'll make the fewest mistakes and you understand it step by step better. I make the choices I make because I think the calculus and maybe even the resulting algebra is a little simpler. You might decide differently because you make more mistakes doing it one way versus the other. That's a decision you have to make on your own, and you only get the information you need to make the decision is by working enough problems to see how your mind works. In any case, I chose to turn it back into the first derivative back into a fraction with a positive exponents and apply the quotient rule. Well, again, we've done the quotient rule over and over again. I'm not going to make a big deal about it here. If you're still having trouble and struggling with the quotient rule, you need to go to the side and practice that as a separate skill. But if you apply the quotient rule and simplify somewhat, you'll get negative 12 times the quantity x squared plus 3 plus 48x squared all in the numerator over the quantity x squared plus 3 all cubed. If you simplify that a little bit, multiply the negative 12 through the parentheses and collect like terms, you'll get 36x squared minus 36 in the numerator, and you can factor that 36 out if you like and write it the way I wrote it here, which is 36 times the quantity x squared plus x squared minus 1, all over the quantity x squared plus 3 cubed. If you had just written it as 36x squared minus 36 in the numerator, that's fine, but it looks better in factored form, and you're going to be plugging numbers into the second derivative, so it probably makes even more sense to go ahead and factor that 36 out. In any case, we have the second derivative now in a fairly simplified form. That's what we need to determine the x values that will give us the interval for the concavity interval check. So going back to the guidelines, we want to find out whether second derivative is 0 or where the second derivative is undefined. I decided to tackle the undefined part first. If I think about undefined values, when you're dealing with a fraction, the undefined values, unless there are some radicals present, the undefined values come out of the denominator. And here you can see the fraction is just a polynomial over a polynomial, so the only undefined values will come out of the denominator. And in this particular case, this denominator can't be 0. Think about it. The denominator is something squared with 3 added to it and then cubed. We'll just try to make up a number where that doesn't come out positive. If you take any number you want, whether it's negative or not, square it and add 3 to it, it's going to be positive. There's no way you can come out with 0. So there are no values that make the second derivative undefined. So we can take that off the table. Now you look at the numerator. The numerator is, when you're dealing with a fraction, the numerator is where a fraction can be equal to 0. So all you have to do is look at the numerator. Well, it's easy to see. You could have even factored that x squared minus 1 as a difference of two squares and written it as x plus 1 times x minus 1. But without even doing that, you can see that when you plug either 1 or minus 1 into that numerator and square them, you're going to get a positive 1, and 1 minus 1 is 0, and 0 times 36 is 0. So it's pretty easy to see, without making a big deal out of it, that the only places you have to worry about for concavity changes are when x is 1 or when x is minus 1. Those are the values that break the number line into intervals that have to be checked, which will ultimately produce what I call the concavity chart. So I put minus 1 and 1 on the concavity chart, and I check the second derivative, not the original function, not the first derivative. Concavity is determined by the second derivative. So I'm going to choose test values in each interval. So I go take a number to the left of minus 1, maybe minus 2, take a number between minus 1 and 1, say 0, and then take a value bigger than 1, say 2. This should look awfully lot like what we were doing earlier with the increasing, decreasing. So the set of skills that you need to do these problems is really the same set of skills as you needed for the first derivative test. So now I want to test in each interval. I'm not going to go step by step on the arithmetic. You have to practice that yourself if you struggle with it. The nice thing is I don't really care about the actual number that I come out with. I just care whether it's positive or negative or not. If you plug minus 2 in and simplify, you'll pretty quickly see that you get a positive answer. That's all I care about. So that means I get positive second derivative in that interval. A positive second derivative means concave up. Then I go to the second test value. That's 0. Again, plugging it into the second derivative, calculating. I don't actually care about the exact value. All I care about is that it does come out negative. So in the middle interval, the concavity is negative, which means concave down. And then I move to the final test value, which is positive 2. Again, I get a positive second derivative. That means concave up. This should look very like what you did with increasing, decreasing charts, except now you're doing everything with the second derivative. So what I can say is that on the interval from minus infinity to minus 1, and from the interval from 1 to infinity, I get concave up, and between minus 1 and 1, I get concave down. If you actually looked at the graph, you can see these inflection points appear when x is minus 1 and when x is positive 1, and the function is concave up, holding water between minus 1 and 1, and it's concave down, spilling water on both sides. If the tangent line to a graph exists at a point at which the concavity changes, then that point is called the point of inflection, or sometimes just called the inflection point. Just to get it into your head visually, that leftmost graph is a place where the function starts off holding water and then starts spilling water. In other words, it starts out concave upward, it ends up concave downward. The point where it changes is your point of inflection. The second example does exactly the opposite. It starts out concave downward, spilling water, and then it changes to concave upward, holding water. That point of inflection is where the change happens. The third example goes from concave up to concave down. The only reason it's pointed out separately is that happens to be a place where the tangent line is actually vertical. That means the derivative would be, the first derivative, which would be the slope, would be undefined at that point. So if you want a formal definition of point of inflection, if a continuous function has a tangent line at a point where its concavity changes, then the point is called a point of inflection. This definition should make it pretty clear that at such points as these, the sign of the second derivative changes. So if we want to locate possible inflection points, we need to find out only the values of x for which the second derivative is 0, which the second derivative is undefined. We've already practiced that. I just want to emphasize that this is what we're doing, and that it mimics what we did for finding relative extrema in critical numbers. That all deals with the first derivative, but the process is essentially mimicked again to do second derivative stuff, which determines concavity, which determines inflection points. It's a similar process dealing with the second derivative instead of the first derivative. So you think of the first derivative as being increasing, decreasing, and relative extrema. You think of the second derivative as being concavity and inflection points. But the process for doing those things is very similar. And I've said this before, but again, it's important. If the point c comma f of c is a point of inflection of some function f, then it's going to be true that either the second derivative is 0 or the second derivative is undefined. Let's do another example. It says, discuss the concavity of the graph f of x equals x to the fourth plus x cubed minus 3x squared plus 1 and find its points of inflection. You should be really happy anytime you're given a function that's a polynomial, because some of the complexity goes away. The derivatives are straightforward. There are no places where the derivative is undefined, the second derivative is undefined. It's strictly a matter of things being equal to 0. The undefined part goes away because for a polynomial function, f and all its derivatives is defined on the whole real number line. It's only where they can be equal to 0 that's going to be a thing you have to worry about. So again, we're looking for concavity and inflection points. So we go to the second derivative, but we have to get through the first derivative before we can get to the second derivative. So we start off with the original function, take the derivative, power rule, power rule, power rule all the way across. Then take the second derivative. You're going to set that second derivative equal to 0. So at some point, if this is a quadratic, you're going to end up factoring, or at least trying to factor it. Turns out here, if you factor out a 6, you get 2x squared plus x minus 1, and that factors itself into 2x minus 1 times x plus 1. If you're having algebra issues rather than calculus issues, you need to take that as a separate problem or something separately to work on, and go off and work on that, and then come back to the calculus part, because the algebra is going to be the mistake-laden area for a lot of people, and you need to work on that, because doing the calculus itself, especially with a polynomial function, is very straightforward. So in any case, I know I'm going to end up setting that equal to 0, which is the reason I went ahead and factored that. If you set the second derivative equal to 0 now, since you've already got it factored, you can see that there are only two places that you're going to get a 0. That's when the 2x minus 1 is 0, and that gives you an answer of x equal to 1/2. And then when x plus 1 equals 0, and if you set that equal to 0, you see the other one is the x equal to 1. Excuse me, x equal to minus 1. So that tells you how to create your concavity chart. You take the numbers you found, put them on the number line in the correct order, and then do test values. So you take something to the left of minus 1, something between minus 1.5, and then something bigger than 1/2. Whenever possible, choose numbers that make your calculations easier. But you're always going back to the second derivative. So don't forget, you're plugging into the second derivative. You're plugging in right here. Or you could go back and plug in here. It's just easier to plug in to the factored form. And when you do that, you're going to get in this case 30, you don't really care that it's 30, you just care that it's positive. A positive second derivative means you're concave up on that interval. Then you move to the second test value, which is 0. You plug 0 in, you end up with -6. Again, the main thing you're interested in is that's the negative number, which means you're concave down. And then finally, your last test value is 1. You plug that in, you end up with 12, which again is a positive number, which means it's concave up. So you have your concavity chart. The problem asks you to discuss the concavity and define the inflection point. So as you're discussing the concavity, what you're going to say is that it's concave up on the ends from -infinity to -1 and from 1/2 to infinity. And then it's concave down in the middle, which is from -1 to +1/2. It also says now to find the points of inflection. Those are just x, y coordinates. You already know the x coordinates. So if you want to find those inflection points, you already know that you're going to be looking at -1 and +1/2 because those numbers came from setting the second derivative equal to 0. Because it's polynomial, there aren't any places where the second derivative is undefined. So it just comes down to finding y values. Now this is an issue that causes students trouble too. Whenever you're choosing y values, remember these are y values that you're trying to calculate here. Y values. You go back to the original function. The original function is y. F of x and y are the same thing. So you go back to the original function when you're calculating y values. Not to the first derivative, not to the second derivative. Anytime you're calculating y coordinates, you go back to the original function, which tells you what y is. Again, if you plug in -1, you end up with -2. So that's the point, -1, -2. And if you plug 1/2 in, calculate, you get 7/16. So you have 2 inflection points. If you really want to see what the graph looks like, you could see it here, and you can see the inflection points at -1 and at 1/2, and you can see the concavity matches exactly what we said it was. Practice, practice, practice. There's nothing inherently difficult about any of this, but you do need to practice, especially if you have algebra skills that need to be honed. I thought I'd throw in one that wasn't a polynomial because it highlights the fact that everything's not going to be a polynomial, but it also highlights, probably more so than a polynomial, your need to have your algebra skills up to par, because you'll get stuck in the morass of the algebra if you're not careful and pretty good at it. So it's something worth thinking about, especially when you're dealing with functions that aren't polynomials. Having said that, we want to know where it's concave up and concave down. That means we've got to find the second derivative, which means we start off with the original function, get the first derivative first. That's a quotient, so you use the quotient rule. I'm going to assume that you can get through this, but it's the same quotient rule you've used now dozens of times. When you simplify the numerator, it turns out very nice, though. It comes out to be -4 over the quantity x squared minus 1 all squared. Remember, we're going for the second derivative, so now we have to take the derivative of the derivative, and this is where you have to be really careful. The -4x is like the high, and the x squared minus 1 quantity squared is the low. You do low d high minus high d low over low low, or low squared. And remember, when you square a square, it's going to end up being a fourth. Just be careful. Now you can simplify this a little bit. I can take this -4 and put it out front, which is where you normally put it. And then here you've got a minus, which is going to end up being a plus. Then beyond that, you've got a 4 times a 2 times a 2, which will be 16. And you've also got an x times another x, which will be x squared. So if you clear all that up, you'll end up with the -4 times the quantity x squared minus 1 squared. Then you've got plus, because a minus is plus, and 4 times 2 times 2 is 16. X times x is x squared. And then you've got that x squared minus 1 sitting there. And it's all over the same denominator. Now here's where people get confused as well. Start multiplying things out. Remember, we've seen multiple times that when things are in factored form, it's easier to set them equal to 0. So why would you want to multiply out the numerator when you really want to factor it? So my suggestion is to look for common factors and not multiply it out. For instance, I see a 4 here, and I see a 4 inside that 16. And I see an x squared minus 1 here, and I see another x squared minus 1 inside of that quantity squared. So I know I can get a common factor out of that. So leaving the denominator alone right now, I can factor out that common factor of 4 times the quantity x squared minus 1 and simplify what's left. So if I take the 4 out of the first term and take one of the x squared minus 1's out, what I'm left with on the inside is the minus sign, which didn't come out, and the other x squared minus 1, which didn't come out. In the second term, I took a 4 out, so from that 16, if I took a 4 out, I'm left with 4. I took the entire x squared minus 1 out, so it's gone, and that x squared is still there, so I get 4x squared. Be very careful here. And if you distribute that minus sign, you get a minus x squared, but then you've got a plus 4x squared, so that's going to be minus x squared plus 4x squared will be 3x squared, and that minus a minus makes a plus 1. You have to be really careful. Look closely and practice. Also notice here that I can do some dividing out. There's an x squared minus 1 factor up top, and there's an x squared minus 1 to the 4th down bottom, so I can get rid of that x squared minus 1 up top by dividing it into one of the ones down bottom, so I end up with a slightly simpler expression for the second derivative, and it's nicely factored. I could actually factor the x squared minus 1 into x plus 1 times x minus 1, but I really don't think I need to. Feel free to do it if you want to, but you can see that either plus or minus 1 is going to make that denominator 0 without factoring. It's up to you. You could actually do that. I don't think it's necessary. But I also noticed that this is similar to something we did a little bit ago. You've got, except it's in the numerator this time, there's no way to make x squared multiplied by 3 with 1 added to it ever equal to 0. Because when you square a number, it's never going to be negative. The least it could be is 0. When you multiply 3 by something that the least it can be is 0, then the least that 3 times something that could be 0 could be 0. But when you add 1 to it, it's going to be positive. So there's nothing you can do to the expression 3x squared plus 1 to ever make it equal to 0. It can't happen. So there aren't any values where the second derivative is equal to 0. However, there are values that make the denominator equal to 0. This is actually the reverse of what we had in an earlier problem where it was the denominator that could never be equal to 0. That means there were no values where the second derivative could be undefined. Now it's reversed. There are values where the second derivative is undefined. There just aren't any values where the second derivative is equal to 0. But it's the same process of thinking it through. What makes the denominator equal to 0 are either plus or minus 1, so those are the values that will make the second derivative undefined. So I don't get anything from the numerator, I only get things from the denominator, but I still have to break my concavity chart up based on those values. So plus or minus 1 go on my concavity chart. I take test values, maybe a minus 2 to the left of minus 1, a 0 between minus 1 and 1, and a 2 to the right. Plug them into the second derivative, always concavity, second derivative. You get a positive value when you plug a negative 2 into the second derivative. That means it's concave up. Plug 0 in and you end up with a negative 4, which is a negative value. It means it's concave down between minus 1 and 1. And then finally, when you plug 2 in, you get a positive value, which again, concavity is up. So if you're looking at the concavity on these intervals, on the extremes from minus infinity to minus 1 and from 1 to infinity, you get the concavity being up, and in the middle between minus 1 and 1 you get down. Now I've done 2 examples where it's been that down in the middle and up on the extremes. It does not have to be that way. It's just a coincidence in the examples I've chosen. I will say one more thing. It really has nothing to do with the question they asked me, because they just asked me about concavity and I've answered it. But had they asked me about inflection points, I would have to say there aren't any, because even though you get x equal plus or minus 1 down here in this step. Those are values where not only is the second derivative undefined, they're values where the function itself is undefined. If you tried to plug either plus or minus 1 into the original function, you'd get undefined because you can't divide by 0. And if you think back to your earlier algebra, those are vertical asymptotes. When you graphed rational functions, you identified those as vertical asymptotes. So there are no inflection points because the only points you're testing aren't even in the domain of the original function. So what you'd have to actually say, had they asked you that, is that those values aren't in the domain of the function, which means they aren't possible inflection points. There are places where the concavity might change, and in fact, there are places, we found that there are places where the concavity changed, but they aren't inflection points. So in mentioning that last part, I went beyond what the question asked for. I just wanted to point out, had they asked for points of inflection, you would have had to say there aren't any. They didn't, and that's probably why they didn't ask. Inflection points can't be calculated if the values aren't in the domain of the function. Pretty obvious. Now, the second derivative test you think of as mimicking the first derivative test, except you're dealing with concavity. But it turns out there's a totally different use for the second derivative that I want to point out. It's actually encapsulated in something called the second derivative test. So even though we usually think of the second derivative as a tool for determining concavity and finding inflection points, it can actually be a substitute for using the first derivative test. There are cases where it fails, and I'll show you how that works. But when it works, it's actually faster most of the time than doing the first derivative test. So the second derivative test is an alternative to using the first derivative test for increasing and decreasing that fails on occasion. And I'll show you an example of that. But when it does work, it's typically a little easier, than doing the first derivative test for extrema. It works because if you think about what we know about concavity at extreme values, think about it a minute. If you've got an area of concavity downward, any relative extrema there is going to be a maximum because it's spilling water there. It's kind of like an upside down cup. It would spill water. That's a maximum. So anytime you have a relative maximum, if you check the concavity there, it should be concave down. It should be spilling water. On the other hand, if you've got an area where an interval where the function is concave up, it's going to be holding water. And that's going to be a relative minimum every time. If you check the concavity around a relative minimum, you'll get concave up. That gives you another way to determine whether a relative extreme value, in other words, whether a critical number is a max or a min. Now, I said this test can fail on occasion, and I'm going to show you that in an example. But when it does work, it gives you something that's simpler to do than the increasing decreasing chart. Just to put it in focus, let's just make it pretty clear by just listing these steps. If you start off with a function and the first derivative is 0, in other words, you're going to get your critical values, and the second derivative exists on some open interval that contains that critical value. If the second derivative at that critical value is greater than 0, meaning it's positive, a positive second derivative means you have concave up, which means you have a relative minimum. So positive second derivative tells you have a relative minimum. A negative second derivative tells you have a relative maximum, because the second derivative being negative means you're in an interval of the concavity being down, and if the concavity is down, you're at a maximum. The third step is where the test can fail. If the second derivative is exactly 0, you have to go back to the first derivative test. So you're using the second derivative test as an easier way to determine maxes and mins, but when it doesn't work, you have to go back to the old tried and true method, which is the first derivative test. Here's an example. if I ask you to take the second derivative test to find all relative extrema of this function, it's just a polynomial. It's always nice when you have a polynomial. You don't have any undefined function values or derivative values. So what you want to do is find the critical numbers. Remember, when we're talking about relative extrema, max mins, we go to the first derivative. The first derivative is going to be negative 15x to the fourth plus 15x squared. We're eventually going to need the second derivative to test those relative extremas. So I'll go ahead and calculate it because it's easy at this point. But the second derivative would be negative 60x to the third plus 30x. Now you can wait a bit to calculate the second derivative if you want to, because we really have to go back to the first derivative and find those critical numbers. I went ahead and did the second derivative just to make the contrast that the first derivative deals with the relative extrema, the critical numbers that we did earlier. Second derivative is for testing. If you're using the second derivative test, it's going to be used to test those relative extrema. But the fact of the matter is, we aren't through with the first derivative. So let's go back to the first derivative. And I know that if I'm going to set it equal to 0 to find the critical numbers, I might as well go ahead and factor it. You see that there's a 15 in both and a x squared in both. And if you want to factor out a negative 15 instead of a positive 15, you can. Seems like it makes sense here. If you factor a negative 15 out of negative 15, you're just left with a 1. And if you factor x squared out of x to the fourth, you're left with an x squared. If you factor a negative 15 out of a positive 15, you're left with a negative 1. And you can verify that by realizing that negative 15 times negative 1 gives you the positive 15 back. And then that x squared. Now, if you want to, you can further factor x squared minus 1 as a difference of two squares and make it x plus 1 times x minus 1. But my contention is, fine, do it if you want to, but you can see right now that what's going to make that first derivative equal 0 are pretty obvious. If you put a 0 into the thing, you're going to get a 0 from here, because 0, once you put a 0 in for x, 0 times anything is 0, but you're also going to get a 0 if you put in either plus or minus 1 here. Because when you square 1, you get 1, and when you square minus 1, you get 1. In any case, however you want to approach this, you eventually got to get to the fact that there are three critical numbers, 0 and plus or minus 1. Those are your critical numbers. Now, if we were using the first derivative test, we would do our increasing-decreasing chart and find the maxes and mins that way. This problem asks us to use the second derivative test instead. So what we have to do with the second derivative test is take these critical values and plug them into the second derivative and look at the concavity. And that's an alternative to using the first derivative test. So if you take your test for relative extrema to be the second derivative test, it says to take the second derivative and plug these numbers in. I decided that before I plug the numbers in, it's going to be a lot easier if I do some factoring, because if you go back to negative 60x third plus 30x, cubing those numbers and then multiplying by 30 on another one and adding all that stuff together looks to be a little more difficult than if you just factored out the negative 30x, and now you're going to get products that are probably easier to calculate. So you don't have to factor the second derivative to plug these numbers in, but I do recommend it. I think the arithmetic's easier. In any case, if I test x equal to 0, that just means I want to plug 0 in for x. If you plug 0 in for x, you end up, see what I mean? It's pretty easy. 0 times negative 30 is 0, and then 0 squared is 0 times 2 is 0, and 0 minus 1 is minus 1, and minus 1 times 0 is 0. Not too bad. But notice that that's the case where the test fails. You're back up in here in case 3 now, where the test actually failed. So for that particular critical value, we're going to have to go back to the first derivative test. But put that aside and let's march on. Test the next one. The next one is minus 1. If you plug minus 1 back into the second derivative, remember we're plugging into the second derivative, you end up with 30. 30 is a positive number. That means you're in case 1 up here now. You're in case 1 where the second derivative is positive. That means you've got a relative minimum. Now we've tested 2 out of the 3 critical numbers. Test the last one. The last one is minus 1. The last one's positive 1. Plug a positive 1 in, you'll end up with negative 30. That puts you into case 2. And in case 2, you have a negative second derivative, that means you have a relative maximum. So the instructions were to use the second derivative test to talk about maxes and mins, and we were able to get 2 of the 3 done with the second derivative test. But whenever the test fails on a critical number, you have to go back to the first derivative test. So we're not quite done. In a perfect world, we would have gotten an answer for all of those and we'd have been done. We would have found our relative maxes and mins and we'd be done. But whenever the test fails for a critical number, for that particular critical number, you have to go back and test it using the first derivative test. So as soon as you get through with the process of the second derivative, if you have a failure, a test failure, you have to go back to the first derivative test. That means you have to build your increasing, decreasing chart, just like we did back in the earlier stuff, except we only care about being around 0. But you do need to put the other 2 values on the chart, because when you're using test values, you still want to stay inside these intervals. You don't want to go way out here somewhere. You want to stay inside of here. So your test values still need to be between 0 and -1 on the left and 0 and 1 on the right. So you do need to put them all on there, but you don't have to test them all. The only one you have to test are the ones around 0. You just need to make sure you don't go beyond to the left of -1 when you're doing a test value, nor to the right of +1 when you do a test value on the other side. So I chose between -1 and 0, I chose -1/2, and between 0 and 1, I chose +1/2. So you plug your test value, -1/2, into the first derivative now. Remember, we're doing the first derivative test now. We're not doing the second derivative test, so you've got to be careful. We're going back and plugging into the first derivative, -1/2, the first test value, into the first derivative. Remember, we're checking using the first derivative test now. So you're plugging back into the first derivative, not the second derivative. We were using the second derivative test, and it worked for 2 of the 3 critical values, but it did not work for the other ones. We have to go back to the first derivative test. So now we're checking into the first derivative. You have to really be on top of it and think this through, because you'll make a mistake if you're not careful. So we plug -1/2 into the first derivative, and you end up with, again, you don't care the exact value. You just see that you get a negative times a negative, which is positive, which tells you that you're in an area where the function is increasing. Remember, the first derivative tells you about increasing, decreasing. So the left of 0, the function is increasing. Then you take your second test value, which is 1/2, plug it in, and it turns out you get, again, the same thing. It's positive, so it increases on both sides. Well, you have a relative maximum if you get increasing on the left and decreasing on the right, and you get a minimum if it's decreasing on the left and increasing on the right. But if it goes up, up, or down, down, you have neither. So the place where the test failed was at x equal to 0, and in doing it by the first derivative test, we find out that it's neither a max nor a min. Now, just because the second derivative test failed does not mean the answer is going to be neither. It could still be a max or a min, but it just didn't happen to be. It turns out that it happened. It turned out that it was neither, but it did not have to turn out to be neither. So I did this second example primarily to show you how important not only the algebra skills are, but even your thinking skills about, am I dealing with the second derivative at this point? Now I'm back to the first derivative. And when I'm doing y values on some problems, I'm back to the original function. You have to practice this. None of this comes naturally to anyone who's just watching someone else do it. You have to practice, 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 practice. So if I do want to find the inflection points, I know I have a relative minimum at -1 something, and I know I have a relative maximum at 1 something, but to find those somethings, I have to get the y values. When I want the y values, I've got to go back to the original function. So now I'm looking back up here at the original function. Plugging into those, I end up with -1 calculating out to be a -2, and 1 calculating out to be a +2. So it turns out that I have a relative minimum at the point -1, -2, and a relative maximum at the point 1, 2, and it turns out that value at 0 was neither. You can see that you have to practice this. This is not something you can just watch someone else do or that you can just cram in at the last second. It really does take practice. There's no shortcut. If you wanted to look at the graph and see that it corresponds to what we found, that there was in fact a minimum at the point we said it was, there was a maximum at the point we said it was, and there was a place where it wasn't max or min, and we caught that and said that it was neither. I want to end with a couple of application problems, and then it's up to you to go practice this stuff. Suppose the cost given in dollars for ordering and storing X units is given by C is equal to 6X plus 900,000 divided by X. What size order will produce a minimum cost? And we want to round the answer to the nearest whole number. First of all, when it says minimum, you know you're going to be taking the derivative. It says minimum cost, so we'll be taking the derivative of the cost function. Now the cost function has a fraction in it where the denominator is X. I would highly recommend rewriting that to make it a negative exponent. So instead of writing it and instead of leaving it and using the quotient rule, you'll end up using the power rule, which is much easier. So if you write that 900,000 divided by X as 900,000 times X to the minus 1, the derivative is fairly simple. Minus 1 times positive 900,000 is negative 900,000, and then you decrease the power by 1, which makes it minus 2. Now once you do it, you probably want to change it back because eventually we're going to have to set that equal to 0 and find the critical values. So it's probably worth changing back. Like I said, why did I find the derivative? Because I wanted to find the critical numbers, which means I've got to set the derivative equal to 0. Well, if you solve that, you can multiply through by x squared and clear all your fractions, and then add 900,000 to both sides and divide by 6, and that comes out to be x squared equals 150,000. If you take the square root of 150,000 and round it to the nearest whole number, you'll see that that's 387. Now, technically, we haven't proven that that's a minimum. That's where the second derivative test comes in. We can use the second derivative test to really confirm and verify that really is a minimum. What you have to do is you have to take the first derivative and take its derivative to get the second derivative. And notice I went back to the form of the derivative where it was written with a negative exponent because that's the easiest form of the first derivative to differentiate. So just to encapsulate what I've done, I got 387. I think that's going to be the answer, but to prove that it actually is a minimum, I have to do the second derivative test, or I have a choice of doing the second derivative test, and in order to do that, I have to take the second derivative. So if I take the second derivative of 6, I get 0, and then if I take the second derivative of the second term, I get a minus times a minus is plus, and then I take 1 away from the minus 2 and get minus 3, and then I can rewrite that with a negative 3, push it down and make it a positive x cubed in the denominator, and now I can evaluate it at 387 and see. I don't really care what it is, I just need to know that it's positive, and if it's positive, that means it's a relative minimum because the concavity is up. So now I have verified that 387 is the order size at minimized cost. So this whole second thing I just did here was the use of the second derivative test, which is why they threw this problem in when they did. But it's just to comfort me to make, I need to be 100% sure that this really is a minimum rather than a maximum or neither. And that just makes me feel better. I had a feeling that the answer was going to be 387 before I did the confirmation. The confirmation was more for my comfort level to make sure that it wasn't something hadn't tricked me, and I thought it was going to be a minimum, but it really turned out to be neither or a maximum. But I figured it would be 387 before I did the second part. Now, pay attention to the difference between this example and the one I'm about to do. This problem asks for the minimum cost. This problem asks for the minimum average cost. That word average changes everything. The previous problem said to minimize the cost. This problem says to minimize the average cost. Well, what is the average cost? The average cost is the total cost divided by the number of units you're producing. In other words, when you're averaging your test scores, you add them all up and get the total and then divide by how many there were. So when you see average cost, you've got to take that C and divide it by X. So watch out for that. If you see average cost, you don't just deal with the C function, you deal with the C function divided by X. So that's the average cost. Now, if it were me, I would divide that up into 3 fractions and divide the X into each term separately. And that gives you 3 different terms here. And you can see that X goes into X cubed and leaves an X squared here. The X is completely divided out in the middle term, just leaving with 30. And then you've got 11.6 over X in the third term. And I would immediately write that as 11.6x to the minus 1, because I know I'm going to have to take the derivative of it, because when they say minimize, I know I'll take a derivative. So as soon as they say they want to minimize something, I know I have to take the derivative of it. So far I haven't done any calculus. All I did is the average cost, and that's all algebra. I had to use the algebra to change the cost into average cost. That's the function I want to minimize. So that's the function I have to take the derivative of. Simple derivative. I won't belabor that, but I will say that I would like to change that x to the minus 2 as being, just throw it in the denominator and make it x to the positive 2, so I end up with, on the last term being 11.6 over x squared. So I want to take the derivative and set it equal to 0. If I multiply both sides by x squared and then solve for x, I eventually want to solve for x, but in order to get to x, I've got to first solve for x cubed. That means I've got to simplify that. 11.6 divided by 0.016 happens to be 725, and then I want to take the cube root of 725. And again, if you don't know how to do that on your calculator, that should be a side issue for you to deal with. I think that's going to be my answer, but to be absolutely 100% certain, and the reason they put it in this section is they wanted you to verify that really is a minimum. So I used the second derivative test. The first derivative I've already calculated, and again I want to use the form of it that's easiest to differentiate again, so I'll use that form of it. Get the second derivative and plug in and change the negative exponent to a 1 over the power, positive power, and then plug in the number I'm trying to test. Plug the 9 in. I don't need to know the exact value, I just need to know whether it's positive or negative. It's pretty clear that that number comes out positive, which means it's concave up, which means it really is a minimum. So the number that I thought was going to be the answer, which was 9, now I'm absolutely certain that 9 is the number that minimizes the average cost per unit. So while you're practicing your skills, honing your skills, make sure your algebra is up to par, make sure your arithmetic is up to par, that you know how to use your calculator when it's necessary. You also need to just practice the thought process, going through the steps, using the second derivative chart. The concavity chart is similar to producing the increasing decreasing charts, but that you're using the second derivative instead of the first derivative. Remember what the second derivative test does for you. It's an alternative to the first derivative test. You could really just use the first derivative test all the time and not use the second derivative test, but when it works, the second derivative test is actually more efficient. And in these last two examples, make sure you understand the difference between minimizing the cost and minimizing the average cost. Puts a lot of things on your plate. Please, please take the time to work, make mistakes, back up, fix your mistakes, get help when you need it, but spend the time on task. It's nothing that's going to come to you in a dream. You've got to work hard for this. Let's end with an important application in economics. It's called diminishing returns. In economics, the notion of concavity is related to that concept of diminishing returns. If we think of a function where x measures some input in dollars and y measures some output in dollars, if you draw a graph of that function, if you see this type of behavior where you have concavity upward to the left of a point and then concavity downward to the right of a point, in other words, you have an inflection point where the concavity is up on the left of it and down on the right, that's an indication of a problem that will have an answer in terms of diminishing returns. What the setup for that is, if you take, because the curve is increasing so much more rapidly before you get to that point of diminishing returns, each additional dollar of input returns more than the previous one. In other words, that's a good thing. Increasing your advertising, for instance, if you're advertising your product, might increase your sales enough to make it worthwhile. On the other hand, once you get past that point of diminishing returns, you don't get as much return for your dollar. Spending a little bit more money maybe on advertising doesn't increase the sales that much. That idea is the idea behind the point of diminishing returns. And that point, which is basically an inflection point, which is exactly an inflection point where the concavity is up on the left and down on the right, is your point of diminishing return. Typically in economics, increasing your investment beyond that point of diminishing returns, is considered a poor use of capital because you're not getting that much out of it anymore. Whereas beforehand, it seems to be a worthwhile investment. Let's illustrate that with an example. By increasing advertising cost X, measured in thousands of dollars for a product, a company can increase sales Y, also in thousands of dollars, according to the model below, and we want to find the point of diminishing returns for this product. So the equation is Y is equal to negative 1/10 X cubed plus 6X squared plus 400, and that equation is valid anywhere between 0 and 40. The point of diminishing returns involves taking the second derivative. We've got to get the first derivative first. So the first derivative, just the power rule. So you're going to get minus 3/10 x squared plus 12x. The second derivative would be minus 6/10 x. I reduce 6/10 to 3/5. And then the derivative of 12x is 12. So you get the second derivative, set it equal to 0, and solve for x. So it turns out that x equal 20 is the x coordinate of the point of diminishing returns for whatever this product is. Now, if you want to actually verify that it satisfies the condition of being a point of diminishing returns, it has to be concave up on the left and down on the right. So technically, you should check this to make sure it really does have that behavior. And if you take a test value on each side, you'll find out that if you plug, say, a test value of 1 into the second derivative, you get a positive value. That means it's concave up. That's good. That's what we're looking for. If you take a test value to the right of 20, you could use 21, but why not just use 30? Seems like it'll be easier because of the 0 on the end. You'll end up with a negative number, which is concave down. That's the behavior that's indicative of a point of diminishing returns. Concave up on the left, concave down on the right. So x equal 20, and you can look at it from a graph, is the point of diminishing returns, or it's the x coordinate of the point of diminishing returns. So we still need to find the y coordinate. So you plug back into the original function. Remember, whenever you compute y values, you go back to the original function. If you plug 20 in for x and calculate, you'll get 2,000 for the answer. So the point 20, 2,000 is the point of diminishing returns. Now, be careful when a problem involves diminishing returns, because sometimes they don't actually ask for the point of diminishing returns, or maybe they don't ask for just the point of diminishing returns. For instance, even though the point 20, 2,000 is the point of diminishing returns, they might ask, either instead of or in addition to that, they might ask something like, what advertising cost is required to reach the point of diminishing returns? Remember, the advertising cost is the x coordinate, and we found out that x was equal to 20. But this is, according to the problem, x is measured in thousands of dollars. So if I'm looking for what the cost would be, it's not $20, it's $20,000. So do be careful about not only exactly what they're asking for, but make sure you've got your units right. Similarly, they might ask, what would the sales be at the point of diminishing returns? Well, remember, the sales are the Y, and they're also measured in thousands. So the answer is not 2,000, it's 2,000,000, which is 2 million. In other words, add 3 more zeros. So just be careful when you're doing these problems to, first of all, know exactly what question you're answering, and also if there's a units issue, make sure you deal with that as well.